in a lab, what happen? We can easily do this experiment. This experiment is there, but of course you are not going to do that one. Okay, shall I proceed now? This one. So what are the few questions we'll ask it? What Einstein asked, what happened? We'll just ask ourselves. Which one will first undergo decay? We don't know. Then what is all are unstable? Yes, all the atoms are unstable and belong to same active substance. The first thing is what is telling. So they're the first thing. Then next again. The moment at T equals the substance is available, first what happens? One will undergo decay. The 37 will never undergo decay. Suppose say at T equals 0, nucleus 1 undergo decay. Nucleus 30 or any number 33 may never undergo decay. May never undergo decay means what is the lifespan of nucleus 1? So therefore, lifespan of nucleus 1. Shall I put 0? For what time it will survive? 0 seconds. Lifespan, all of you, lifespan. For what time? Till now, I survived for 45 years. I don't know what is my lifespan. Survival. So what is the survival time of the nucleus 1? 0. What is the survival time of the nucleus 3? I think I'll mark. I'm just consider these two. So what is the lifespan of next year? Lifespan of nucleus 33 is infinity. Huh? Sir, how come both are made up of, both are having same kind of, both are unstable? We don't know that. What is the lifespan of remaining all other nucleus inside that will vary from 0 to infinity? Lifespan of all other nuclei will be between infinity to 0. Sir, can we identify which particular nuclei will not undergo decay? You said 33. We can't find out. Which will undergo now only decay or after, so now at T equals 0, it is formed. After 1 day, sir, whether 19th nuclei will undergo decay, we don't know that. So how to study this? So don't bother anything, don't bother which will undergo decay. Just you go for the amount of substance, that's all. So it's like a probability. We are entering into the concept of the probability, that one. Able to understand? So if you can get this idea, I think it'll be in far better position. So what it's telling is like, instead of trying to break our head, just take the amount of substance. So initially at T equals 0, what is the amount of substance? N naught. I'll get into the next part. The second discussion. So what I have is N naught substance. How many nuclei are there? N naught nuclei. How to calculate number of atoms? I think you know enough of chemistry. Even I too also know. So let me say that at T equals 0, the number present is how much? N is equal to N naught. At any instant of time. Some decrease, no? Let the number present be N. So it won't decrease, no? Those which are, see, like again you can say, like, sir, this atom, will it vanish? No, it will become some other substance, some other element. Is that okay? Uranium 236 will become uranium 235. Let's assume that one. So it becomes some other element. Don't think that that will vanish from there. It no longer it is called as that particular element here. So therefore, the number of active samples will decrease here. So what it's telling is this particular number of decays depends on what? Depends upon the initial number present. So here, so if you see the rate of decay, that one. So dn by dt. This is directly proportional to the initial number present. And since it's a decay, no, I'll put negative sign. I think your chapter got over, radioactivity got over. The rate of decay depends on what? Depends upon the number present. So this to remove this proportionality, I'll introduce constant called as decay constant. And for different elements, it will be different. Then dn by n equal to minus lambda dt. So the rate of decay depends on what? Depends upon the amount of substance. Now you see that one. What is this dn by dt? Number of disintegrations per second. And what is lambda into n? This is also the same unit, no? So what is lambda into n? Number of disintegrations per second. What is lambda? Lambda is decay constant. So dn by dt, what we should call number of disintegrations per second, or number of decays per second, anything, or rate of decay. It is directly proportional. Means you take 1 kg substance, you see more alpha beta particle. You take 0.1 kg substance, you see less. So therefore, the number of decays per second, that what I notice depends upon amount of substance. So I'll bring it. And for different substance, I see that dn by dt is different. So therefore, I brought the lambda. So let's integrate now. This will be dn by n equal to minus lambda into dt. At t equals 0, what is the number? N naught. At any instant of time, let it be n. So this will become log of n by n naught minus lambda t, or this n by n naught equal to e to power of minus, and n is equal to n naught e to power of minus lambda t. What is n naught? The number present at any instant of time t. What is n? Number decayed or number survived? This is a number survived. Number of nuclei present at any time, or the numbers survived of n naught. How many are there? N are present, number of nuclei present at any time t. How to calculate the number decayed? Number of nuclei decayed. I'll write n dm. This should be equal to n naught minus n. So this will be n naught e to power of minus lambda t. Okay, so the number decayed what will vary with the time in this particular fashion. So this particular, I'll multiply the lambda on the both sides for this equation. What is lambda into n will become activity. So therefore, now look at the activity. The activity, some books they use word R. So I'm using A naught as symbol. So the activity, that one. So what do you mean by this activity? Let's plot graph so that we'll get some better information. So if I plot first it is n naught. This is what n survived, no? So at t equals 0, the number survived is n naught, and with the time, we'll get like this. What is this n? Number present at any time. At different places, I'm representing number of nuclei at time t. This is what the n I'm showing. So you look at this. What is this substance? All the nuclei. So it's an active sample. You take 1 kg substance, all uranium-238, and all the nuclei are unstable. You take any nucleus is unstable, and all the nucleus, what happen? All the nuclei, they want to attain stability, but what happen? Only few will come forward to attain stability. And if you look at the whole substance, initially I see more radiation. Then with the time, what happen? The number of alpha beta particles emitted by that will decrease. So what happen? The substance will lose interest in what? In undergoing the decay. Able to understand this activity, or if I plot this, then the number decay, no? Oh, sorry, this is. I should not multiply here. So for activity, I'll multiply this. Now we have here only you write it ND. No, I think this you may not agree with this. I'll bring one more. I'll multiply lambda on both sides. Now this will become activity. What is activity? The rate at which number of disintegrations per second that will occur. And what will happen to that quantity? You can see decrease the exponent. Means initially the rate of disintegrations will be more. With the time what it keeps on decreases. And when it becomes zero, at infinity. So why do it happens? We don't know that. We are all together what we are able to measure that disintegration. Can we measure? As we are able to measure in lab, you can do. This experiment is there. Not for highly radioactive substance. So one which are not much harmful for our human eyes and skin. No? So that particular radioactive substance is kept, and we have a counter to keep nearby. You can see the display there, and you have to keep on note down for different instants of time. You start counting that, and you can see that particular graph here. So now, why do the substance will behave like that? We don't know. Why some nucleus what happen will come forward to undergo decay, the right at t equals 0. Why they'll never undergo decay? We don't know that. And the same substance. So what do you expect? It should keep on undergo decay. No, I think we expected the curve of this kind. Will I agree? The curve of this kind. So if the curve were like this, what does it mean? Or the activity curve, if it were like this, then the rate of decay constant, no, means at first t equals 0, 10 particles per second are emitted. At any instant of time, when the same 10 particles per second are emitted, but not like that. Initially, you say 10 particles per second. So let me plot this activity curve. If you can understand this, rest all mathematics. If activity curve were straight line, then what you would have concluded? For every 1 second, or if it were like this, sorry, what does it mean? For every 1 second open, the number of disintegrations are constant. In first second, 10, for every 1 second, 100 particles are emitted. Even after 1 hour, even after 1 day, 2 day, after 1 year, the same 100 particles per second would have been emitted, but we didn't get any response for any radioactive substance of this kind. Whereof this particular thing. So this shows that the activity itself will decrease with the time, though it is unstable. So how to discuss such a phenomena? We just take the probability. This is brought from probability here. So rather than discussing for one atom, for one nucleus, better discuss for the whole of a substance. Then it'll be much easier for us to discuss, because if you take the atom which will never undergo decay and you keep on make observation only on that, if it undergoes decay after a t equal to infinity, then gone, no. So what shall we do now? So always you should discuss radioactivity for not for specific group of atoms or a given atom. It should be for all substance, is what is telling. Okay, this is about this one. Next, I'll increase temperature. Anything will happen to this curve? No, nothing. I'll increase pressure. Nothing. I'll increase humidity. Nothing. The external parameters again will not influence this decay process. In a simplest way, the external parameters will not influence this decay process. Nothing to do. The external parameters will not influence this decay process here. Means by varying temperature, density, pressure, humidity, so all those parameters will not influence this graph. You change the conditions, external parameters, you see this graph here. There's one more thing. So the radioactivity doesn't matter like where you perform. It's unstable, it will undergo the decay and finish all. And the number of disintegrations per second will keep on decrease. That's what the third condition will put it. External parameters will not influence the decay process. So I think we need not to bother anything of that kind. Just leave it. So where it is kept, what is the acceleration due to gravity, 9.8, 10, where all you keep it in space or on Earth or any other planet. So what decay should undergo, it will undergo the decay. That's what he's telling this one. Okay, this is the first thing I brought it activity and the number of decays. You will plot the number of decay versus time graph. When I plot this graph, I think it will touch at infinity, no? Number of decay with the time. So here also open the number of decays what happen? When it will become, when the whole atoms will undergo decay at infinity. There's a graph for number of decay here, that one. So when this will become equal to n naught, so when t equal to infinity, that one. So they show that the whole substance will never completely vanish. It takes infinite time here. Let's how to some quantities are needed, no? This particular how to get that lambda, how you measure. So what I do is like, what is the time taken for the number to become half of the initial value? I'll call that as half lifetime. Half lifetime. So as we know formula, n equal to n naught e to power of minus lambda. At t equals 0, it was n naught. After what time it will become n naught by 2. I'll call that as t off. So this will become 1 by 2. So this should be equal to e to power of lambda t off is equal to 2. Or if you send log, take log on both sides, it will be log 2. So what is the t off equal to? Lambda by log 2 it will come. So there's a time taken for the number to become half of the initial value. So what is
And
t?
then 2 by lambda, sir.
Lambda by t off, no? Lambda by t off equal to 2.
Lambda into t half, sir. How by?
Okay, this one. Wait, yeah, I'll check the calculation. The time taken for the number to become half, no? Okay, this is okay. 1 by 2 is equal to 1 by e to power of lambda t to power of 1 by 2. So e to power of lambda t 1 by 2 is equal to, I'll take log on both sides.
Sir, there you took instead of lambda into you took lambda by, sir. E per lambda into t half equal to 2.
Fourth step, sir.
Oh, okay, this 1, 2, 3, fourth one. Okay, this one. E to power of lambda.
It should be into, sir.
Sorry. Yeah, fine. This will be lambda t1 of is equal to log 2. Log 2 by lambda will come. Yeah. Now you see this. There's a time taken for the number to become half of that one. It depends upon decay constant. Different materials, there are different constant here. Like that, we can go for average also. How to calculate average? How to calculate average of life? So what is the lifespan of few atoms? 0. And what is the lifespan of other atoms? It is infinity. So when I go for the average, no, I think that average will become equal to only 1 by lambda. This I think may not be very important. Just you do remember that may not be. Most of the books, what happened, they derived it. If you want to check it, that one. Half-life is something very important for us. Okay, I'll come for other calculations purpose. So after getting this half-life, so what happened to activity after half-life? A is equal to A naught e to power of minus lambda t, I got it. So what is the activity after half-life? I think the same formula we can use it, no? What is the activity after n half-lives? I'll write it proper. Yeah. Similarly, can we calculate activity after what time the number will become off mean this one. So as we know, n equal to after one time, it'll be like this. After n off lives, what is the number? So shall we put n equal to n naught into 2 power of n? What do you mean by n here? N off lives. Say after one off life, how much the number will become n naught by 2? After two off lives, how much the number will become n naught by 4? After three off lives, the number will become n naught by 8. After like this, n off lives means just I'll put like this. Then similarly, what happened to activity? You multiply lambda. Then activity will become a naught by 2 to the power of n. So what is the activity after n off lives? This is the formula. Similarly, the number decayed after n off lives. The number decayed, what is the formula? N naught minus n. N naught to the power of n. So this will be. Now what you should call this? Number decayed after n off lives. Similarly, okay, there's a thing. Do remember, the number decayed after n off lives means you should not write n naught by 2n. The number present, this is number survived after n off lives. How many nuclei decayed after n off lives? So you should write n equal to n naught 1 minus 2 to the power of n. So these are some generalized formulas which will be exclusive using that one. Of all this activity. So what is activity now? Disintegrations per second. We define like this. Number of disintegrations per second is what we call that one. So once again, I'll write it. It is called as activity. Number of disintegration per second, or number of decays per second. So like this open will introduce a quantity is called like a number of disintegrations per second here. So now if you look at this number of disintegrations, this is something very large, no, practically. So how to express this number of decays per second? So we do have units. Like since the disintegration per second will be very large, so what we do is like a one disintegration per second, we'll call it as a 1 becquerel. So since the disintegrations are very large, so 1 curie, the one unit what will propose it, 1 curie will become equal to 3.7 into 10 to the power of 10 becquerel, or 1 becquerel is 1 disintegration per second. The SI unit for disintegration per second is what? 1 becquerel. I think the pronunciation of this will be BECQEREL. 1 DPS only we call it 1 becquerel. Since I see large number of particles, so to make it unit small, what I'll bring curie. 1 curie is what? 3.7 into 10 to the power of 10 becquerels, or disintegration per second. So this is SI unit for the, you can say SI unit is becquerel. So since it is a very small, like a more number of decays will occur, no, to make it small. So we are bringing the unit called as 1 curie. So most of the answers, if you see we'll express in terms of curie, because we see particles of these many. Suppose in one of the decay, 10 to the power of 14 particles per second, will be given out. So expressing that large number is a big problem. To make it small, we bring the curie idea, this one. So this is about the theoretical